Hi, everybody. How are you doing? I'm okay, thank you. Hanging in there. So we are going to do lab 8 if you want to check that out. Let me take a screenshot of my code and put it on there so it's easy for you, okay? This program is a little longer. Mm, Okay. Let's check out the lab in Canvas. And then let me put my code on there for you. Shh. Okay, 1 second. Let me put the code on there for lab and then we'll get started. So today we're going to do lab 8, which is faster multiplication. We worked on multiplication and division last time, and we are going to do a better program today. Okay. 1 second, and then I'll go into screen share. Let's see.
Apparently, I cannot download the Quiz 2 review homework.
Okay, let me double check it for you, okay? Hold on 1 second. Lab 8, part 1. Okay, I'm going to save this right now, and you should be able to see your code in a second. And then we'll go over that. Let me double check your assignments and see how it's linked. Sorry for the confusion, just hang tight. Okay, let me redrop the files in there. Okay. Okay, so I think it should be, I'll fix accessibility stuff later. All right, so let's look at the lab. The lab this week, we are doing multiplication in LC-3. So I'll walk you through the process now. Let me go into screen share here. And hopefully my internet is not going to be spotty again. So I posted the code there for you just now. You can take a look at that and we will go over. I added the comments, so I will go through each line. And this week we are going to work with saving to register and restoring from register like what we did last week. And we are going to call on the subroutine similar to what you did last week. But in this week, we are only going to work with the multiplication. So we are not going to do the division this week, okay? So in your lab, let me know this real quick. Let's talk about what's required in our lab. So in our lab this week, we are going to multiply, and we need to make it faster using subroutine, and we are going to use what's called the shift and add method. Keep in mind that you will have to test your input just like what you've been doing. So you need to set the value at the location for your input, which is going to be 3100 and 3101. So before we run the program today, make sure that we go to that location and set your X and Y to a certain hexadecimal value. Then after you set your values, you would then go run the program and go to hex 3102 to see your output. It will not appear in the console because it will only show up on the simulator. We did not convert it to ASCII to show up on the console in the program. And you can if you like, but that will take another section of code. So we're simply going to look at the simulator, set the value, run the program, and then look at the location for XY product. Then similar to last week, we are going to use a subroutine, and in this one, we are going to do a mult one. This is a little bit different than last week in that we are going to shift and add, okay? So it's slightly different. And keep in mind that we are not controlling overflow. So when you set your value to be large, be careful because it will only extend to the bit size for the word instructions. We are not controlling overflow. So let's talk about the algorithm so you can understand. So in shift and add algorithm, we would multiply X, for example, in this one is 13 in decimal, or convert to binary, it will be 1101. And then for the Y is 43, okay? Now you see that this is an immediate value, and when you add it, what you can do is you can shift and add it. So when we do the shift and add method, this is what it looks like. Just like how we multiply binary in the past, in the first week that we covered, we talked about binary multiplication. We would multiply and then we get, for the first digit, we would multiply from the right and we get an output for that. then on the next digit, we are going to shift left one column. So that way we would then eventually, after we shift all the digit that was multiplied from the second part right here, we would then add them up together. So in this week, the subroutine is going to deal with the bits and the shift and add in the binary equivalent. Okay, so keep in mind that we're using bit shift add. So if the bit is 1, the multiplicand is added to the product, then shifted to the left by 1 position. If the bit is 0, then the multiplicand is shifted left with no addition is performed. So if you look at how we multiply, we take the value from the multiplier and we multiply. So if I have 1 multiplied by the top line, which is a multiplicand, what happens is it's exactly the same, right, as the output for that line. Okay, so we multiply it by the 1, we bring the multiplicand down, and then for the next digit to its left, for the multiplier, which is 0, then you would then have the 0 place on the right, and then you shift it, but you don't add this row. You do not add, because if you multiply 0 by the multiplicand, everything will be 0. Okay, sorry about my dog, he's thirsty. So we don't add this line because it's 0. Then the next digit is a 1 for the multiplier. Then we multiply that by 1. We would indicate that because it's the same value. So you see on the third row, we would add the 2 0 at the right because we're shifting now 2 position as it is a third digit. So again, you have 1 0, 1 0, 1 1, which is exactly like the multiplicand. So this line you're going to add. So you're going to add this line, this row, and then this row. You're going to skip anything that has the 0. Then we have the last, the 1 digit here. And so what we will do is, again, we would shift it left 1 more digit, and then we place the multiplicand there. So when we add this as binary, so the 1 would drop down, this one would have a carry to the column, and then the carry would apply here with an additional carry to the next column. So when you add everything together with the binary addition, you would then get this result. So this technique is what's seen already in the binary multiplication. So now we would take these steps or the algorithm and we would implement it in LC3. Okay, any questions so far? Okay, so for the next part, it explains that when you're looking at the value for X and the value for Y, you would envision it as bits. Okay, they should be in binary because that's what the computer sees. So when you set your value for input for X, let's say I set it as a hex 2, then that would be, right, 0 0 0 0 1 0. Then when I set the bits for Y, it would then convert it to binary as 0 and 1s. So that way it would represent the bits, okay? And the Y is going to be your multiplicand, okay? So if we're looking at the Y value, okay? So the multiplier X and the multiplicand Y, the Y would be the multiplicand and the X would be the multiplier, okay? So when you set that, keep in mind that it does the conversion in our program, and when it multiply, it's going to shift and add for any bits that are on, which is 1. It's going to skip that when it is 0. And we have to think about that in LC3 because if it sees that bit as 1, right, we would check for positive. If it sees that bit as 0, we would branch with the 0. Okay, and you know, it seems more complex in the description, but if you think about the machine level, all it is just going to check whether that bit is on or off. And with that, it is much faster than if we go the other route like what we did last week. So here, it talks about how multiplication by 2 is equivalent to a left shift. So when you're looking at a digit 2, it will be a left shift to the next column because the second bit is on, as the most least significant bit is a 1. Okay? So now let's look at how we would put it together with the pseudocode that they gave us. So when you compute the product, which is going to be your xy, your y is going to be multiplicand and your x is the multiplier. So like a regular C++ program or a C program, we have to initialize that product, right? You would say product is equal to 0 before you enter the loop, because you have to have that variable ready to store as it loops through and it adds it into that variable. Okay, so here we initialize the product. So all that is if you LDI, if you load a register with XY or the label XY, then you clear that register to make it a 0. And then what we will do is we will implement a for loop, and we would start with an index 0. We're going to go to 14. This is going to allow us to exclude the sign bit. Okay. And with that, it's going to allow up to 14 placement of bits. Okay. And when it does that, because we would assume that it's going to move and shift, and then it adds for every bits that are on. So with the for loop, we then have to nest an if. So we would say if x of I is 1, right? We said that when the bit is on, it would add the value, okay? Then what we need to do is we need to have the product is equal to product plus y, because y is the multiplicand. Now, pause there for a second, come back up here. So if the bit is 1, then it's exactly like the multiplicand. So you would take whatever the value of the multiplicand and you put it into the product xy. Okay? And because it's a group of bits, we have to implement the for loop to be able to get through each of the bit and place that into the location where the product should be so we can add it. Okay? And so now back down here, then what we would have is when we work with y, y is going to be y plus y, as we would then have to shift each bit to its left. Okay, so this is how you can implement the shift add procedures or algorithm in the product to find a product for multiplication. So in the next part, what it's telling us is that when we check whether the least significant bit, right, for example, the register 1 is 0 or 1, we can implement something like this. Just as what I mentioned, we would see how these two lines, they clear, okay? So here you clear register 2, you add 1 to register 2 to initialize, and then you would then add register 1 with register 2. Remember that register 1, right, is the multiplicand, and we wanted to check if that significant bit is a 1. So when you add a 1 with a 1, it's going to give you a 1 with a carry. If you add, right, so if you add a 1 to it, and if it's a 1, then it won't branch for the 0. And when we said earlier, if it's a 0, we're not going to add. If it's a 1, we are going to add. So when we branch it for the 0, so if the least significant bit is a 0, then it's going to go to the is 0 section. And we simply use the branch Z to check whether it's a 0 or not. If it's a 0, we won't add. If it's not a 0, right, we will add. Okay. And in this case, it's only going to be positive as we look at binary as +1. So in here, what we can do is we can check real quick, send it to is 0 label, and then again, we would then test the next bit, which is in the next register. So in this case, what you're doing is you're setting up your register to hold all these bits, right? And when you're checking from the right, which is the least significant bit, that will be your register 1. If it's a 0, we're not going to add it. If it's a 1 on the next register, we are going to add it. Okay. So after we check the register 1, then we would then clear, we would AND R0, R1, R2, and then check again for the 0. Okay. And if you look at the AND operator, when you AND anything with a 1, what happens? Okay. Anytime that it's a 1, it's a 1. When you AND it with a 1, the output is going to be a 1. Right? Okay. So then when you adding the register 2 to itself, the only bit for the register 2 that is 1 shift to the left of the 1 position. So the way that we can move things around is through register. And what we want to do is when we want to implement how we can check from the right to the left through the register. Okay. Any question? So as you can see, the programs are going to get a little bit more complex, right? We want to introduce you to different techniques because in LC-3, when you iterate, even if you use iteration, it's a different deal, right? You have to take a look at how that number is represented and what type of processes you want to implement. Okay. No question on that? All right, let's talk about the subroutine. So in the subroutine, we're going to call this mult1. And when you're writing a function in C or C++, what you see is you have to pass your variable, right, as parameter. So that way it can operate with the values that's stored inside that variable. So in here, what it talks about is your parameter is going to be your variable X and Y, which is passed to that function, okay, via the register 0 and 1. Then the result, what it's going to do now in this part, this is going to be just a subroutine now, right? The other part is separate. So the result is going to be the register 2, and the multiplication should work even if the parameters are in the negative numbers. So we talked about last week how we treat sign, right? When you look at decimal values, when you multiply, they are positive and then you sign it later, okay? So we have to convert it to positive and then we have to sign it if it's a negative at the end, just like last week. So it says here that the multiplication should work even if the parameters are negative, and to achieve this, use the same technique as 5.4, which is the previous lab, and handle the sign. We talked about that last time. We treat it as positive, and then at the end we sign if it's a negative. So the register should be used for the subroutine should be saved and restored. So we can set all that up at the beginning, and then we restore that at the end. And all that is the temporary location where you would be able to put the values in there, and then later on you can retrieve it. Okay. All right, so what we need to do is we are to write the program. And when I grade your assignments this week, I find that most of you did really great in testing your value. Some of you just write the program and simulate it one time, right? How do you know the limit of your program, right? When you write your program, and I hope that when you write your program to submit to employers and workplaces, you should check the limitation of your program. You should evaluate your algorithm and see the capacity of your algorithm, okay? So I need for you to spend a little time because we're only doing one exercise per lab, right? Understand how the subroutine works. Go back to the program, go back to the lab description on how it explains the shift and add procedure, and see if you can digest it and be able to absorb it. And that's important for me because at the upper division classes, they don't care if you know it or not. They just go into the concept and you have to know it. Okay, so to be successful in this, we have to know the basic and move forward. So I need you to explain the subroutine and how that's implemented. You and identify the system call and the services in the program. And we talked about that last time. When you call, that's when you do the JSR, right? Jump to subroutine. That's what it is. So what it does is mechanically it sends the simulator to your subroutine section, which is your function definition. Okay. Then answer, what are the primary functionality of the of system calls and services? Okay. So what is it doing there, right? You know, if you can't be specific, just at least summarize and tell me what's happening in that section. Okay. And then identify the program call related to instructions, vector, and register. So what am I looking for? Trap, okay? The pseudo instructions, the trap, the register that are related to that. And you know that when we return from functions or subroutine, it uses R7, okay? It has a store and it traps out. So it's gonna actually store that somewhere and then pull it so that way it gives you the return value, but then we save it to a register so we can later restore it. Okay. Then for question 2, I want you to test the values. And again, I give you the decimal, so convert it to hex and test it. Look at the 3102 location, which is your product XY, and see if your outcome is accurate. Is it handling your negative number? Okay. And how is it handling the larger positive value? And I do read your response in your lab, right? So explain to me what kind of challenges you have, okay? Because that way I can assess it and say, okay, my students need time to spend on this. So the feedback that I got from Lab 5 was many of you attempted, and I'm so proud of the month program. The challenges you have was the multiple input. So when you come back from spring break, I'm going to spend a little bit of time explaining the solutions to you. And there are quite a few of you that got successfully working program for exercise 2 in lab 5, which makes me super proud. Okay. So you're doing a good job overall. You understanding some of the concept, but I want to make sure that we address the challenges and I can help you with whatever I can before we hit the project. Okay. And I wanted to see if you look into alternate solutions to overcome your challenges. And there's some of you that mentioned to me that the reason why I submit this late is because I was trying to work it out. And I appreciate that very much. Okay. So look for ways to overcome your challenges. And then if you can't, I want to know about it because that way I can help you in the specific. Okay. So answer these questions and make sure you test the value. Please give me some screen capture showing that you test some of the values. All right, any concern or questions relating to our task?
I just like to say, just so everyone knows. In the code, towards the loop, you have BRZ is 0, but it's supposed to be not 0.
Let me see. Did I skip? I skipped a section. I'm sorry about that. Hold on 1 second. Okay, let me check my screen capture. 1 second.
Oh, you have an extra piece of code in there. I see. Also, it was supposed to be like that, huh?
Yeah, there should be 2. There should be is 0 and not 0. I should have is 0 and not 0 on there. 1 second. Let me check my screen capture, okay? I'm just, when I'm in a hurry, sometime I might miss something there. Oh yeah, I apologize. I did miss the is 0 section after loop. So let me add the second part correctly, okay? Yeah, there are 2. So let me fix that for you guys. Thank you for bringing that up. Otherwise you guys will have an incomplete program.
Yeah, no problem.
I was rushing to do that and I was trying to get all your grading done. All right, so here, let's go back to the lab and let me edit it and fix the second part. So the first part up till loop is okay. Then for the second part, we're going to insert a new image. And let me label it for accessibility. Okay, LC-3, part 2 of lab 8 program. Double check. Double check. Okay, good. I think we're good. I save it now, so it would take a second. So you can reload your page and it should show it now. Okay, let's go back to screen share. Okay, so sorry, after loop, there should be an is 0 section. And then after that, you would have a not 0 section. Okay, so let's start from the top. So when you look at this, right, we know that we have to start at, or we have to originate at hex 3000. Any of the function call needs to happen early. So we need to do a JSR molt 1. Okay, so when you use subroutine or function that happens, that needs to go at the top of your program, just like last week. After it calls, then it's going to do a halt. Okay, and I have a section for save register. Come on, buddy. That would represent the binary. Okay, so like what we said earlier, we are going to use 1 register per bit. Okay, so if you start with the store first, then you would do a load after. Okay, so when we begin, we need to make sure that we associate the temporary location to each register, starting with register 0. And keep in mind that LC3 only has 8 general register from 0 to 7. Therefore, we can only store from 0 to 7. So to start the molt 1, which is our subroutine, we would start with the save register. And we would try to keep it uniform so we know exactly which is which. Okay. Then here I comment that register 0 is going to be X, register 1 is going to be Y, and we store value to register locations for these. Okay, so what we did was we create an array of temporary location to begin with. All right. Ooh, I just caught an error. Give me 1 second. I caught an error. You guys see it? Oh, actually, that's fine. Okay, hold on. Let me double check something real quick. Oh yeah, that's fine. It's fine. Sorry. Okay, so this part right here at the top, I'm going to point you to where that is in the document. It's this part right here. Okay, we were doing this part right now. Okay, we're going to sign 1. We're going to put 1 to sign. Okay, because when you look at the sign value, right, doesn't it have a bunch of 1s in the front for the negative, right? So what we're going to do is we're going to put that 1 there to represent a sign. Okay, so that's what we're doing in the next couple of lines. And then we're going to do an if x is less than 0, then x is going to be negative x. So we're going to convert it to positive. Then we're going to, when we're going to do a sign is equal to negative sign, and we're going to do this part like what we did last week. Okay, so right now that's what we're doing. So coming back here, we're going to clear register 7. Why am I doing that? Because if you're looking at a value, okay, so let's say that if I have 20 or -2, okay, when I look at the binary, it would have these 1s in the front, okay, these 1s in the front. So the 1 here is going to represent the sign for me, and then the rest of this is going to be a value, right? So what we're doing is, if you're looking at starting from the right, which is going to be the lower register, and we're going to go left. So register 7 is the end. That's going to be our sign. Okay. So here is where we're going to load. We're going to add the 1 to register 7. So that way we would represent that as a sign. Then we are going to load X to register 0. And we want to initialize, right? We want to initialize. So here you can do a clear, right? Or you can do an add 0, the same. So we would initialize our 0 as 0. And we want to check if X is positive, right? Or 0. So here is where you wanted to see if X is greater than and equal to 0, then you're going to send it to pass. Okay, what am I talking about? If we look at this right here, right, we have to make sure that we check this right here to make sure that we convert our X to positive. Okay, so at this point, what we're doing is we're going to make sure that we check to see if it's positive. We will branch to positive if positive number. Then we want to subtract 1 to test for sign. So because earlier we add a 1 to it, then we would subtract 1. So when you do a 2 complement, the first complement, when you knot it, it actually is 1 less, okay? And when you sign it, this is why the second complement, we add a 1, okay? So now if we wanted to test for sign, we go in reverse. So we have to subtract a 1, okay? Understand? Any question with that? All right. So here we would subtract. Yes.
So
Fine.
with the LDI inside of the subroutine, the parameters and return values here are in the memory rather than in the registers.
The parameter, because yes, because you know why? Because you use X as parameter inside the function. Like if you define a function in C++, if you set it X inside the parentheses, this is what we're doing. And it's because X is going to be represented with all of these bits, not by itself. So when it loads X, it loads it as a parameter. So you're right. Yes, we need to have load X inside the function or the subroutine because X is represented as bits. Other questions? Okay, and X is the multiplier now, right? So we're checking if it's 0 or 1 and so on. All right, so here we subtract the 1 and then we want to now work with possible value of X that will be negative. Okay, so now we would do a first complement of R0 when we knot it here, and then we would add a 1 so that way it's the 2's complement, so R0 is negative X. Okay. Then in the pos, we're going to load Y, and Y is our multiplicand, the top row. So, and Y is used as parameter. It's Y inside the XY function, okay? The mult function. So here is why we need to load it here. Instead of in the last program, you load it at the beginning. So now what we're going to do is we are going to clear register or initialize 0 for register 1, which is Y is equal to 0. And then we want to branch for 0 positive, and we would then send it to pos 2, which is the next section. And this is the nest condition. Okay, so we are going to nest the if in that now. Okay, so flipping back to here, we are doing this part right now. Okay, got it? Okay. Then, so we talked about pos 2, then on the next, we're going to subtract 1. We are going to do the 2's complement to represent negative Y, because Y could also be negative. Okay. So this part is similar to what we've seen last time that came from the last lab. That's with the nested condition with X, Y, positive and negative. Okay. Any question? All right, pos 2. In pos 2, we are going to clear register 2. We're going to clear register 4, and we're going to clear register 5. So in this one, you can clear as you go, or you can clear them up front. So I chose to clear them up front so I can just add in different things to it. Okay. Register 4 is going to hold the count. And pause there for a second. I wanted to take you back here. Okay. We are doing the count for the for loop, 0 to 14, which is 15. Okay. That's what register 4 holds, 15. So we can count, and we're going to subtract 1 every time we go. And every time it loops. So there is the 15 for the count. So we would count in for the for loop. And then I would add 1 to register 2. So this is when we would add shift. So we would add hex 1 to register 2. And then we would copy it to register 6, where register 6 is going to be Y. So I copy Y to register 6. Why is that? Because I don't want to overwrite the value, just like what I did last week. Okay, so when I add a 0 here, it's a copy register. Okay, any question with this? Okay, again, pos 2 represent this part. Okay, then we still have to nest it. Okay, then the next part for loop. For the loop, we are entering the loop and we're going to do an AND R3, R6, R2. Remember in the example earlier when it branched to is 0, they show you how you can AND it to make it the least significant bit to check, right? The least significant bit, which is the most right-hand bit. Okay. And if it's a 0, we're not going to add. If it's not a 0, we are going to add. Okay. So now we're entering the for loop. Okay. So here is when you check the least significant bit, you would AND it again, not add, AND. Okay. And we would apply the AND operator rule here. So when you branch it with the 0, if it's a 0, you're going to send it to is 0. And then we are going to do an add R5, R5, R0. We're going to copy X to R5. Okay, why are we doing that? Because we're going to restore it later. Okay. Then on the next part, you are going to have the is 0, because since we branch here, we would have a label called is 0. And then we would do a shift. So in the document, it explains to you that when you add the register itself, it would force a left shift if it's a 1. Okay, so we would force a 1 shift to the next column by adding that same register. So here I do add R2, R2, and put it back into R2. Okay, and then again, since X is in register 0, I do the same thing, add R0, R0, 0 to shift for X. So do a left shift for X. Then I would subtract 1 from my count, because now that would be 1 loop as it shifts 1 place. Okay. And as long as R4 is a positive, if the count is still positive, it's going to come back to loop again, and it's going to redo the same thing for every single bit. If it gets to the 0, it's going to jump to the next, it's going to go to the next line, and it's going to apply the condition for the branch, which is for not 0. Okay. So as long as it's a 0, right, it's going to check, copy the X, and then when it's a 0, it's going to do a shift left, and it's not going to add, right, because we just shift, we don't add for the is 0, and it's going to do that 15 times. And then after it finished the loop, it's going to go to the next line, and here is where we would start the condition for branching. So now, since we checked for 0 earlier, we would have to branch negative and positive for non-zero, for not 0. Okay. And we want to use a register to represent possible negative value as a product, because you can have a positive multiply it by a negative, you would get a negative product. So we want to sign that. Okay. So here, if it's not 0, right, it could be negative or positive, then we would want to have the first and the second complement for R5, which represents negative product in output. Then in the not 0, we wanted to take whatever that was the product, which is in register 5, and we're going to store it to P, or you can call it XY. I just stick to P because I was following their pseudocode. Then again, we would then load the register back because we store them at the beginning. So we restore register here, right? All our registers that would represent 8 bits or 1 byte. And then we would return, and that would complete our subroutine. So because we have registers that were for save and restore, we would give it actual values that, well, they're just subsequent to the rest of your code, but it's not a permanent address like the X and the Y. So here, when you save register, you can give it hex 1, hex 0, hex 1, hex 2, hex 3, hex 4, hex 5, etc. And you would fill those. Okay. Then your X, Y, and P, this is the permanent address where you can set the value is the XY. So hex 3100 and hex 3101 is where your Y is. And then your product is the output of the multiplication. And that the end is the end of your program. So it seems more complex than it is, but it is not, right? So if you look at the loop closely, it just iterates through that, okay? If it's a 0, it shift, no add. If it's a 1, it shift and add. Okay, any questions with our code? All right, so after I have my program written, I would open up my simulator, and I know I'm repeating, but some of you, I noticed that you maybe don't remember how to test your program or don't test your program. So open up your simulator and then load the program. Okay, and I put everything in a subfolder so I can find it quickly. Then what I want to do is before I run it, I need to set value. Okay, so click set value button. We're going to jump to hex 3100. And let's say that I'm going to add hex 2. Okay, for X. And then I'm going to make Y. Let's say we're going to do a 4. Okay, so after I set my values, then I click run. Okay, we're not going to see anything in the console. So what we need to do is we need to jump to hex 3102. Okay, and it shows that I have an 8, which is what it's supposed to do, multiply, but it just shift and add the bits. So what do we really know about this from now, right? Like after we write this program, anything that you multiply, the computer does shift and add bits because it's much faster than interpreting everything, convert it back, all of that. Okay, so now you see what the machine is doing when it's looking at multiplication. it interprets it as a binary value, and it skips the 0, it adds the 1 and shift. Okay, and if you wanted to check out your X, Y values, right, I set X for 2, Y for 4, and my output is an 8. Okay, and like I said earlier, if you're working with the larger value, when you're trying to play with this program, we don't have overflow control, so that might be an area, the limitation area that we need to look at, right? So we can add something in our code to have the overflow. We touched on this a little in a couple lab ago, but in this lab, it didn't require that. So what we did was we just simply write the subroutine and, you know, use XY as parameter in that subroutine when we call it, and we implement save and restore register, and then we can set the value to check. So an expectation for your project would be that I will require you to have a subroutine in your project program. You will be required to save and restore registers depending on the program of the selection in the project option, but all programs you can use save and restore register. And then some of the little stuff like labels, you know, how to use your instructions, operands and opcode, etc. Okay. So now if you wanted to jump back and look at your code, right, you can go back to hex 3000, and that's where your program starts. Okay. And then you can take a look at your program, what it's doing there. And then recall that, you know, if you wanted to step over, you can step over and then place a toggle breakpoint so you can see what's happening in each step. Pay attention to the top and then look at what it's doing. So we have a halt, so it's just after it multiply, it's just stop, right? And then it finish out the program. Okay. Any question? So this is a different approach to multiplication. And that allows you to see what the computer actually sees and what it does when it multiplies. So no questions, huh?
So this is what the computer does when you just do a multiplication in C++.
Yep. Or you type your calculator like 2 times 4 or 2 times 5,000, right? Because everything breaks down to binary, and so if it sees a 0, it shift no add. If it sees a 1, it shift and add.
Of course, this is just integer multiplication. I suppose a floating point is a bit more complex.
Yeah, so LC-3 doesn't do float, but other assembly actually you can implement float as it uses C compiler. So in that, you still have to think about how you place the point, floating points. So what do I mean by that, right? Just like how in last week we talked about quotient and remainder, okay? If you think about a program that does like a division, like last week, we have to have a placement for everything. The data doesn't just magically appears, right? It doesn't dissolve. We really have to tie it to a memory location. So the floating points, the decimal points subsequent to that, it needs to pull that from somewhere. So when you use assembly, you have to think about, okay, I'm going to have an area where I'm going to hold the the value that is significant, which is before the period or the point, and then an area in the memory location where it holds the rest. Okay, so when you say float in C++, right, the compiler does the work for you already. So what you have to see from a compiler standpoint is that it needs to associate different memory locations. So we can, if we manually do that, we would say when the user, when it stores that float, it's going to take the value in the front of that point and place it here, and then subsequently would be all the decimal value following. So I have worked with NASM, Microsoft ASM, a little bit of ARM, and depending on the type of language, but other more modern language handles floating points. However, the concept is that even when you work with C++, Java, Python, etc., you really have to create a variable, a container, which is associated with an address. Otherwise, right, you have to type it and tell the system what it is. So when you type it, the compiler or the interpreter sets up that location for you, right? In assembly, we don't have that. We have to manually do it. So when you work with that, you have to think about that, okay? And think about what the computer is doing at that step and the subtask behind it. And this is the point in this class, is the logic and implementing the logic, like how the computer would solve that problem. So I have
So
a
I
chat.
see here we did not do any handling of overflow, but if this were floating point, you'd increment the x base.
Yeah, so you would have to implement additional locations or a way to control that, right? It would have to stop at that size. So Beethoven asked if assembly, is there assembly for trigonometry? Yes. So if you work with the more modern assembly language, which takes this concept and further implement it, right? So if you can understand LC-3 when you read ARM or other assembly program in a slight different syntax, you're gonna see it, right? So you would use like ARM64 or when I worked with Microsoft ASM, which used like the older x86, for Intel, um, it has some functionality for higher mathematical calculations because it's able to handle images and things for the interface, so you can add some of the GUI stuff on it. So yeah, so some of the later stuff you would be able to, and almost all of them use C compiler, and then or they have their own, right? Many of them have emulator and things like that. So if you want to practice ARM, there are a lot of different tutorials. Just keep in mind that they are different. There are different versions of ARM. So 64 is now what's being used, but if you're working with Cortex-5, right, which is the processor for many of the smart devices, then it's slightly different than ARM 64. So when you work with engineers, like let's say at companies that produce processor for, I don't know, like they produce like Snapdragon and some of the processor, even Apple, they have their own set of instructions on how it's used, just like how you read documentation for Java and Python. There's slightly different syntax and different ways to use or to use that language. So you just have to check it out, but the concept is still the same, right? In that, when you're looking at from a computer perspective, it's adding binaries all the time.
So for something more simple like LC3, if you want to implement, say, a trig manually, I've been through Math 1B. I know it's using an infinite series, and you have to sum so many terms of it.
Right. So going back to the Beethoven question, if we're implementing trigonometry, you have to break it down to the simplest level, right? Like dissect it and piece it down to the very small subtask and then work from there. And the way that you would be able to understand the program better is to really understand it at the lowest level. Okay. So so right. So you would then look at how you would be able to look at like how we would compare. What does logarithm mean? What does, what does this mean? When we apply that equation, if we piece it out to the small subtask and see how that would be manipulated with just addition, what can you do with that? Okay.
It's good to know infinite series, since many add in terms of an infinite series.
Right. So it's there's a lot of like math components in all areas of computer science because computer science is math, right? Um, so it sometimes it's hard to visualize, I understand, but you have to be open to alternate way to solve the problem at the simplest level, especially with assembly. Okay. And if we're looking at efficiency, some approach might not be fully efficient, but at hardware level it would need to be at the bit level. Okay, so when you're looking at video adapters, storage devices, all of this is gonna, it has to start from programming at machine level, right? And then be able to, integrate other things like applications on top of it, using operating system with it, and so on. Okay. So if we can come back down to the very basic with that, then we can start elevating it for other things. Because all the bells and whistles stuff, like when I see my students, they're so concerned about putting GUI on their application. But if your program doesn't work and if it's not efficient, what's the point of adding GUI on top of it? Right? Like, so make sure that your program has strong technical solution or algorithm that works, and then worry about the bells and whistle and the prettiness and all of that later on, because that stuff is easy. You can bring in libraries and things to do that. So for some assembly, you can do dot external and then pull the library of people who wrote menus and stuff and add that into your module, and then you can have a complete program. But your program has to be functioning. Okay, so it's very important that you understand subroutine functions, methods, all of this, how to use it, how to use with object oriented. You have to understand how to use set class and subclass in order to appropriately apply libraries. Okay, in general, in programming in general. Okay, so any questions? And then after that, everything else is pretty straightforward because everything is almost have the same concept. All right. So I won't see you until after spring break. I wish you have a wonderful time. Enjoy yourself, have fun, relax. And if you want to catch up with work, you can do that. I will be working on some curriculum. I'm working to build data science program for the district that's going to be shared with Norco, Riverside, and Moreno Valley College. With some math faculty, we're doing the program. So we will have a data analytics certificate in a year or so, and then we will have an associate degree for data science. UC Berkeley is interested in teaming up with us. They are one of the pioneers in data science. So I'm working with one of the department at UC Berkeley to establish some relationship, and we submit quite a few grants for computer science. So we will have a lot of improvement in that area because they hired me to really expand the program and improve. And for you as students, I want to make sure that you have options. Data science is such a hot field right now. So if you do see that down the line, you can get a bachelor degree and get a certificate at community college and find work. But it's just whether you have the skills or not. So we will incorporate big data and more database and statistic, and some of that with Python programming and R in data science. And then the sad thing is I have to put one of my dogs down this weekend. He has cancer and I'm devastated, but it's gonna have to happen. So yeah, it's a bummer, but hey. So if you're done, go ahead and thank you. Go ahead and just type your name into the chat, and then I wish you well for spring break, and I'll see you here the following week. So have fun. Okay, take care.
See you after spring break.
Bye. Take care, Ryan. Thank you. Take care. Thank you. Have a good night, Thomas.